Section 6.3, Conservative Vector Fields. Your homework is problems 106, 109, and 116. Let's begin with curves and regions. Notice I separated this section into 3 parts. So to begin, let's define a closed curve and a simple curve. So in simple words, without having to read that definition, it's simple if it does not cross, and it's closed if it has the same beginning and ending. So here you have some pictures, and it tells in the bottom whether it's simple or not, or closed or not. And we see it's only one of them that's simple and closed. So we see that it's bounded from B to A. It means it has the same beginning and ending point. Now here you have an example. Is the curvature with parameterization R of t equals cosine of t, comma, sine of 2t over 2, bounded from 2 pi to 0, a simple closed curve. So you want to know if it's simple and if it's closed. All right, so I provided the image. If you were to see a question like this and weren't too sure how your image looks, you can go ahead and use your computer and search on Google Desmos graphing calculator and type this in. Once you start typing it, if you put it in parentheses using T, it'll also give you a chance to enter your bounds. And you'll get this image in return. And you'll see that this picture itself, it's closed but not simple. And it's not simple because it crosses itself. Now, another region we need to discuss is a connected region. So let's read this definition. A region D is a connected region if for any 2 points, P1 and P2, there is a path from P1 and P2, right? So P1, P2, there's a path, right? Where the trace contained entirely inside. A region D is simply connected region if D is connected for all simple closed curve C that lies inside of D, and the curve C can be shrunk continuously with a point while staying entirely inside of D in 2 dimensions. A region is simply connected if it has connected and has no holes. So this is our ideal region, is a simply connected region. The others are examples of regions that wouldn't necessarily be simply connected. So here we have another set of examples, and it reads, they're connected, but they're not simply connected. And the other one, they're 2 different regions that are supposed to be one whole region, so they're not even connected. Now, the reason we're working up or talking or setting up this area or space in which we're working with is because we're trying to essentially figure out the work done to get from point 1 to point 2. We want to find the work. That's what we're doing when we're finding these line integrals. Now, the work, what we will discover is that the work is the same regardless of the path you take, as long as you go from point 1 to point 2. Think of, for example, a hiking trail. And that's an example your textbook gives you. You're going to go from point 1 to point 2. You can go directly, or that might not be the most efficient, or that might, in other words, that might be the hardest. So you have another path that will get you there. It might be easier, but might be longer. However, you're going from the same point 1 to the same point 2. All right. Now, I I removed a lot of the examples from this section because they weren't the best of examples, and we're trying to just cover two main ideas. To know if it's um, a conservative vector field, and if so, find some type of a potential function given some type of vector value function. And those are two main things we're trying to find here. All right, so let's take a trip down memory lane. Let's generalize the fundamental theorem of calculus to line integrals. Recall that the fundamental theorem of calculus says that it is a function. F has the antiderivative capital F, then the integral from a to b depends only on the values f at a and at b, right? And I'm sure you've seen this plenty, right? And that's how we define um, our integration. When you see capital F, it means antiderivative. If we think of a gradient vector f of a function f of 2 or 3 variables as a sort of derivative of f, then the following theorem can be regarded as a version of a fundamental theorem of line integrals. Fundamental theorem of line integrals. Let C be a piecewise smooth curve with parameterization R of t, with a less than or equal to t less than or equal to b. Let f be a function of 2 or 3 variables with first order partial derivatives that exist and are continuous at c. Then, the integral of c of the gradient f dot dr equals f of r of b minus f of r of a. And we're skipping the examples that deal with this for the section, and your homework doesn't directly work with these problems either, but it's good to know. Definition of independent path. Let F be a vector field with domain D. The vector field F is independent of path or path independent if the integral C1 of f dot dr equals the integral of C2 f dot dr for any path C1, C2 in D with the same initial and terminal points. The second consequence is stated formally in the following theorem. 6.8. Path independence of conservative fields. If F is conservative vector field, then F is independent of path. Note, suppose C1 and C2 are two piecewise smooth curves, which are called paths, that have the same initial point A and terminal point B. From the theorem above implies equally whenever the gradient of F is continuous. In other words, the line integral of a conservative function, a conservative vector field, depends only if the initial and terminal point of a curve. In general, if f is a continuous vector field with domain D, we say that the integral of C f dot dr is independent of path. Is C the integral of C1 f dot dr equals the integral of C2 f dot dr for any two paths that have the same initial and terminal points, such that we can say that the line integral of the conservative vector fields are independent of path. And again, that's why we went through the whole images in the beginning. This leads to another theorem that's not listed in this text, and it says that the integral C of f dot dr is independent of path in D if and only if the integral from C dot dr equals 0 for every closed path C in D. Theorem 6.8, the path independence test of conservative fields. If F is a continuous vector field that has independence of path and domain D of F is open and connected, then F is conservative. And we will learn how to test for conservative in the future. Theorem 6.9, path independence test for conservative fields. If F is a continuous vector field that is independent of path, then the domain D of F is open and connected, then F is conservative. Now there's some examples not listed of how we can go about doing this, but there's also another method that's listed at the end of the text that's much easier. So we're skipping the test for conservative fields using the initial examples. We have spent a lot of time discussing and providing path independence conservative fields and paths of independence tests for conservative fields, but we can summarize them simply. A vector field F on an open and closed domain is conservative if and only if it is independent of path. This is important to know because conservative vector fields are extremely important in applications, and these theorems give us a different way of viewing what it is to mean conservative using path independence. And whenever you think of anything being applicable, it's your physics. All right, so we're going to continue this thought of conservative fields and how to test to them or test for them. So we're going to take a break. Next part of your text, it leads us into conservative vector fields and potential functions. Let's skip to the end of your text where it begins with testing a vector field. So this is directly from your text. Until now, we have worked with vector fields that we know are conservative. But if we are not told that a vector field is conservative, we need to be able to test whether it's conservative. Recall that if F is conservative, then F has a cross partial property. That is, if F equals PQR, so these are your components of your vector value function, right? It's conservative, then P of Y, or P sub Y equals Q sub X, P sub Z equals R sub X, and Q sub Z equals R sub Y. So if F has cross partial properties, then F is conservative. Now this section is very notation heavy. Don't let this notation throw you off, right? So we have a vector value function, right? So F comma F of X comma Y comma Z. That would be like your let's use a constant A, Y plus B, J plus Z, K, right? Or you can write it without I, J, K with the vector notation. So if they're labeling the first one to be P, the second component to be Q, and the third to be R. So when we see this, it's telling us that we're taking the first component and we're taking the derivative in terms of Y. We're taking Q, which is the second component, second in terms of, we have a little x, so in terms of x, and so we have three different ones to prove for equality. And all those three need to hold true in order for them to be vector valued. I'm sorry, conservative fields. Now, I think it's odd. It didn't list how it would hold for two, for only x, I'm sorry, or for I and k. So we just take the derivative of the other, right? So using their notation, you would have your p in terms of y equal the same as your q in terms of x. Only. That's only if you only have I and j, no k. And this next theorem is almost the same as the one above. So let's do an example. Determine whether or not the vector value field f of x comma y equals x minus yi plus x minus 2j is conservative. All right, so all we have to do is take the derivative of x, well, of the first one in terms of x, and of the second one in terms, I'm saying that wrong. We're taking the first one in terms of y and the second one in terms of x. There we go. All right, so let's go ahead and list it out. So we have our first one, our p and q, right? So we have p of x comma y, which is x minus y. And we have q of x comma y, which is x minus 2. Now we're going to take the derivative of the first one in terms of y. So our derivative in terms of y, well, we don't have a y here, so that's 0. The derivative of y is just 1, so we just get 1. So the second one, the derivative in terms of x, the derivative of x is 1, the derivative of constant is 0, so we just get 1. Now, our theorem says that they have to hold equal. So since they're not equal, so since p sub y does not equal q sub x, f is not conservative. All right, here I use a notation that your textbook has, but we can also use this using that Libin's notation. So let's do another example. So for the first one, we have determine whether or not the vector field is conservative. We have f of x comma y equals 3 plus 2xyi plus x squared minus 3y squared j. All right, so for the first component, we have p of x comma y is equal to 3 plus 2xy. And second, we have q of x comma y equals x squared minus 3y squared. All right, let's work on those derivatives. For the first one, I want to take my p and take the derivative in terms of y. So that's a constant, that's just 0. My y is 1, so we're just left with 2x. For our q, our dq, we're going to take in terms of x, dx. The derivative of x is 2x. There's no x here, so our derivative is just 0. Now here we see that our results are the same. So therefore we can say yes, they are conservative. All right, not so bad, right? Alternatively, using the beginning portion, we would have to go ahead and use our function, work with some integral, and you should get the same result to show that they are conservative. But we can also do it this way. All right, so bouncing back to the middle of our notes, we're labeled as part 3. Conservative vector fields and potential functions. Given a conservative vector field, how do we find the function f, such as the gradient of f equals capital F? All right, to find the potential function f of x comma y of 2xy cubed comma 3x squared 2y squared plus cosine of y, thereby showing that f is conservative. So we have a list of steps to follow. These list of steps are for only 2 components. So when we do this next one, it's going to be a bit more challenging. All right, so to begin, we want to go ahead and take our function. and write our f of x. So we have our first part, we have 2xy cubed. Our second is 3x squared 2y squared plus cosine of y. All right, first we want to do is integrate f of x in terms of x. So let me write that step down. So that we have, if we integrate in terms of x, then that's the only thing we have to worry about. And the integral of 2x is x squared. So we have x squared y cubed. And when we integrate, we need to add our plus c. So we need to write a plus c such that when I take the derivative, it's gone at 0. So it needs to be of everything except x. So it needs to be in terms of y. So we add h comma y. So I'll write a little note of that. Because when we take the derivative, h of y is 0. So that's why there's no x. Because if I take the derivative of x, it should be 0, right? That's why it's h of y. Okay, next, so part 1, integrate p in terms of x. That's what we did. This results in a function of the form g of x y plus hy, which is what we have, where hy is unknown. We don't know what hy is. Step 2, take the partial derivative of g of xy plus hy with respect to y, which results in the function gy of xy plus h prime y. All right, if we take our partial derivative, we get 3x squared y squared plus g prime of y. So we took our partial derivative with respect to y. Now we're going to go to step 3. Use the integration of gy xy plus h prime of y equals q of x comma y to find y prime. Or h prime of y, I said that wrong. So that we have gy of x comma y plus h prime of y equals q of x comma y. So that we have 3x squared y squared plus g prime of y equals 3x squared plus y squared plus cosine of y. So we took two parts. We integrated in terms of x, and then we took the partial derivative with respect to y, right? So those are the two parts we have. We integrated partial derivative in terms of y. So we set those two. Working with those two, we can now set it equal to our functions. So our two functions equal to each other. And we see that g prime of y would be the same as our cosine of y. So this implies that h prime of y is equal to cosine of y. Then h of y is equal to, so if this is our derivative, our antiderivative, if this is h prime, then h would be, the antiderivative of cosine is sine, so we have sine of y plus c. Now as we continue, we're going to let c be 0. So that our final answer is f of x comma y is equal to x squared y cubed plus sine of y, well, plus c of 0, and that would be our potential function. And it's because it works out that we have this, right? Because you see how this only worked because our second component was kind of within the same terms as what we were working with. Okay, let's work with one that has 3 parts. So find the potential function f of x comma y of, I think I meant z, I'm sure I meant z, comma z of 2xy cubed oh no, I'm reading the wrong one. All right, so we have x of, I didn't mean a z as well, of 2xy comma x squared plus 2y z cubed comma 3y squared z squared plus 2z, thereby showing that f is conservative. All right, let's begin by labeling our first part. So we have f of x equals 2xy. All right, let's go ahead and integrate in terms of x. So that if we do that, we have f of x comma y comma z is equal to x squared y plus z plus c, but we don't write plus c because we have 2 other variables, so we write those 2 other variables instead. So we have f of y comma z. All right, then we're going to take this and we're going to differentiate in terms of y. All right, so that we have f y of x y comma z gives us x squared plus f of y x comma, no x, y comma z. So all we did was took the derivative in terms of y, there's just one y there. Instead of writing a prime, we have 2 other cases to keep track of, so we use a subscript of y to let us know we took the derivative in terms of y. Okay, then we want to compare the second component. So for the second component, we have x squared plus 2y z cubed, right? X squared plus 2y z cubed. All right, and we want to go ahead and compare it. So here we have x squared y plus, we can write, I'm sorry, comparing this here. So we have x squared plus 2y z cubed equals f of y, which is x squared plus 2y z cubed.